Have you ever wondered why the universe works so well? Look up at the stars, or simply notice your own breathing, and the same question returns. Why does reality seem so perfectly tuned? It doesn't feel like pure chance. It's as if the cosmos shipped with factory settings that make our existence possible. Are we a miracle, a digital simulation, or the lucky winners of an infinite lottery? In this video, we'll explore the universe's magic numbers. Constants so finely balanced that a small change would snuff the lights out for good. We'll see how unseen forces hold matter together beneath your feet, and how stars once cooked the ingredients of your body through a chain of near impossible events. From the precision of the very first second to the idea that reality behaves like code, we'll ask, was the universe made for us, or are we the astonishing accident? Either way, the answer changes how you see everything that follows. Richard Feynman, one of the sharpest physicists of the last century and a Nobel Prize winner, spent an unreasonable amount of time worrying about a single number. In the 1940s, while working out how electrons trade energy with light, he kept running into a value that refused to explain itself. It wasn't a sprawling formula. It was simply 1 divided by 137. Feynman used to say that every good theoretical physicist should write that number on the wall and lose sleep over it. He called it the greatest mystery in physics, a magic constant that arrives from nature already finished, without showing it's working. We now call it the fine structure constant. It sets the strength of electromagnetism, the force that holds atoms together, makes chemistry possible, and lets light travel through space. Nudge it even slightly, and the world changes. Atoms bind differently, stars burn on another schedule, and life never finds stable footing. What haunted Feynman wasn't only that the constant exists, it was that even the best mathematics could not derive it. The theory could predict what happens once you feed the value in, but it could not tell you why the value is what it is. To learn it, you have to measure reality directly. It's as if the universe shipped with factory settings, and nobody left the manual. Here's a way to feel the oddness. Imagine buying an old radio. You expect music, but the set only works if you turn the dial to one exact station, 137.035. A hair too high or too low and you get static. The number isn't printed anywhere. The radio is simply built that way, and you discover the right setting by trial and error. Modern physics is full of such razor-thin settings. The cosmos rests on constants that look calibrated, where a tiny tweak would bring the whole stage down. And this is only the first warning. Behind it sits a deeper tension, an uneven contest between two giants. Gravity tries to crush matter into dense lumps. Other forces, electromagnetism, radiation pressure, and the nuclear reactions that make stars shine, push back and hold structure open. The mismatch is so extreme that, by naive odds, you might expect the early universe to have collapsed into black holes long before the first planet formed. Yet it didn't. That breathing space depends on countless tiny tolerances. How fast stars fuse, how stable atoms remain, how chemistry builds complexity without falling apart. The point isn't to claim a hidden designer. It's to notice the improbability and ask what kind of universe can balance on such edges. Somehow these enemies cooperate just enough for galaxies to assemble, stars to ignite, and chemistry to turn into biology. And in that knife-edge balance is the real question. How can forces this mismatched still leave room for you to be here, breathing, right now? To see why the universe can feel finely tuned, look at the most uneven contest in nature: gravity versus electromagnetism. At first glance, gravity looks supreme. It holds the moon in orbit and keeps you on the ground. Yet, measured against the other forces, it is astonishingly weak. Electromagnetism, the force behind electricity, chemistry, and the bonds inside atoms, is vastly stronger. The gap is so extreme that physicists sometimes describe it as a 1 followed by a forest of zeros. You can sense that imbalance with a fridge magnet. A small magnet can pin a note to a door, beating the pull of the whole Earth on that scrap of paper. The universe has structure because gravity loses most local skirmishes, yet still wins on the larger scales, gathering gas into stars and galaxies over time. Now imagine turning the gravity dial slightly upwards. Stars would form from smaller clouds and collapse harder. They would burn fuel faster and die sooner. Instead of long-lived stars like our Sun, steady furnaces that shine for billions of years, you would get massive blue stars that blaze briefly and explode. Light would exist, but the window for life would shrink. Turn the dial slightly down and the opposite happens. Gas struggles to compress. Clouds never squeeze enough to ignite sustained fusion. Without stable stars, there is no long-term warmth and no patient chemistry. A dark, thin cosmos follows, where planets and galaxies are rare or impossible. The tuning tightens further inside matter, where the strong nuclear force rules. This is the glue that holds protons together in atomic nuclei, and the margin is only a couple of percent. Make the strong force a little stronger, and hydrogen, the universe's basic fuel, disappears quickly after the Big Bang. Protons fuse too easily, leaving little free hydrogen for long-burning stars, water chemistry, or stable planetary systems. Make it a little weaker, and nuclei fail to hold. No helium, no oxygen, no carbon, no metals. Just lonely hydrogen clouds, unable to build complexity. So we live in a narrow window. Gravity weak enough to let stars live long, but strong enough to assemble them. Nuclear binding strong enough to build atoms, but not so strong that it burns the fuel before the story starts. And even that is not enough. To get you listening to this, stars must manufacture the bricks of life, especially carbon. Carbon production inside stars depends on a delicate resonance, an energy alignment that makes an otherwise unlikely nuclear pathway run efficiently. Without it, you might still have light and heat, but not the chemical backbone biology needs. That weakness is also why you can have both softness and solidity. On the scale of your hands, electromagnetic forces set the rules. They keep atoms at arm's length. They define hardness, friction, and the chemistry of your body. On the scale of interstellar space, gravity quietly adds up. One atom has almost no gravitational pull, but a cloud with unthinkable numbers of atoms can collapse under its own weight, provided the balance is just right. If gravity were stronger, collapse would happen too easily. Stars would be smaller, hotter, and shorter-lived, racing through their fuel before planets had time to cool, oceans to settle, and biology to experiment. Supernovae would be common, but stable. Gentle sunlight would be rare. If gravity were weaker, the opposite problem appears. Matter would remain too spread out. You might get diffuse glowing gas, but not the tight, long-burning engines that drive chemistry forward. So the universe needs a Goldilocks gravity, and it needs it alongside a Goldilocks nuclear glue. Together, they create long-lived stars, stable atoms, and the slow, layered build-up of complexity. Without that slow build-up, there is no room for memory, evolution, or minds. That is why tiny shifts in these settings don't just change the universe. They remove the stage entirely for us. This is where even skeptics pause, not because chance is impossible, but because so many tolerances stack at once. What happened inside the first stars that allowed dead matter to become the chemistry of meaning? You've probably heard the phrase that we are stardust. What people rarely add is that, for that dust to exist at all, the universe had to clear a hurdle that looks almost impossible on paper. Right after the Big Bang, the cosmos was chemically simple, mostly hydrogen with helium close behind. If the story had stalled there would be no oxygen in your lungs, no carbon in your cells, no rocks, no oceans, no biology. For anything richer to appear, stars had to become furnaces that turn light elements into heavier ones. But when stars try to make carbon, nature seems to hit a wall. To build carbon in a star, 3 helium nuclei must fuse in quick succession. The pathway is called the triple alpha process, and it sounds straightforward until you see the snag. When 2 helium nuclei collide, they briefly form an isotope known as beryllium-8. The trouble is that beryllium-8 is extremely unstable. It falls apart almost immediately, so quickly that, under normal odds, it disappears before a 3rd helium nucleus can arrive to complete the carbon nucleus. Here's a simple image. Picture a billiards table. You send 2 balls towards the center to collide exactly where you planned. But by a strange rule, the instant they touch, they vanish. Your task is to strike them with a 3rd ball at precisely the moment of contact, before they blink out. The timing window is so small that you would never bet on making the shot. By that logic, carbon should be rare, and life should have no solid chemistry to stand on. This is where the astronomer Fred Hoyle enters the story. In the 1950s, Hoyle reasoned backwards. Carbon exists in abundance, and living beings are built from it. So something inside stellar physics must be making that triple collision far more likely than naive probability allows. He predicted that carbon must have a very specific, excited energy level, a resonance state that acts like a hidden doorway. With that doorway in place, the 3 helium pathway becomes efficient enough for stars to manufacture carbon in meaningful amounts. Physicists went looking, and the result was striking. The resonance was real, sitting almost exactly where Hoyle said it would be. It wasn't a vague hint. It was a precise match, as if the reaction had been given a handle to grab. And the tolerance is tight. Shift that energy level by only a few percent, around 4% either way, and carbon would not accumulate in stars the way it does. Without carbon, complex chemistry collapses. No DNA, no familiar biology, no rocky worlds rich in organic possibility. You might still have light and heat, but you lose the chemical backbone that makes life plausible. Hoyle was not trying to prove a religion. He was famously skeptical of theological explanations. Yet the elegance of this monstrous coincidence unsettled him, because it looks less like a lucky accident and more like a requirement built into the rules. So yes, we are stardust. But we are stardust because the heart of stars contains a razor-fine resonance that makes carbon possible. And if that feels surprising, the next step is even harder to accept. For stars to form in the first place, the early universe had to survive its opening moment with extraordinary precision. How close were space and time to being erased before they properly began? If stars are the factories of life, the Big Bang was the moment it was decided whether those factories would ever be built. We often picture the universe's beginning as a chaotic explosion, but the physics points to something closer to an extreme balancing act. For the cosmos to survive its first breath, the push of expansion and the pull of gravity had to be tuned with a precision that defeats ordinary intuition. Cosmologists describe this in terms of a critical density. the knife-edge value that determines whether the universe eventually recollapses or expands too fast for structure to form. Imagine the universe as an athlete trying to clear a gap. Jump with too little force and you fall short. Jump with too much and you overshoot wildly, never landing where you need to. In the cosmic version, that initial jump is expansion. If, in its earliest moment, the universe had contained just a touch more matter than it did, gravity would have taken over quickly. Expansion would have slowed, reversed, and everything would have collapsed into a final crunch, a big crunch, where space and time fold in on themselves long before the first galaxy had a chance to form. But if the universe had been just a touch lighter, expansion would have been too violent. Matter would have thinned out so rapidly that atoms would never gather into clouds. Clouds would never ignite into stars, and stars would never build planets. You would get a bleak cosmos, lonely particles drifting through an ever-growing emptiness, rarely meeting, never organizing into anything like biology. What leaves cosmologists breathless is how narrow the safe corridor appears to be. The initial conditions had to be tuned to an almost unimaginable degree, something like 1 part in a quintillion. To get a feel for that kind of odds, imagine dropping a coin from the height of a cruising aircraft and having it land perfectly on its edge, balanced on the blade of a razor, whilst a hurricane is blowing. That is the flavor of precision being discussed. People sometimes summarize it as a number with 60 zeros, but the point is simpler than the metaphor. If the early balance had missed by a hair, the curtain would have come down before the play began. No night sky, no sun, no memories, no observers to ask questions. This isn't poetic exaggeration. It's the mathematical requirement for a universe that lasts long enough to form structure. It means the universe began balance between collapse and dilution, with just enough time and density for complexity to emerge slowly. At that point, the question becomes unavoidable. How did everything fit so well? Are we simply the lucky winners of an impossible cosmic lottery, or is there a deeper explanation? Some scientists answer with a strange but elegant idea. Perhaps there is no mystery at all, because if the universe were not compatible with observers, there would be nobody here to notice the incompatibility. This is the Anthropic principle. It doesn't claim the cosmos was designed for us in the human sense, but it does suggest a kind of selection effect. We only ever find ourselves in a universe where beings like us can arise. And that leaves a final dilemma hanging in the air. Are we genuinely seeing something profound about the universe? Or are we being fooled by a biological filter, mistaking conditions that allow life for a universe made for life? The answer matters because it changes what you believe about your place in space and whether the fine-tuning is a clue or just the price of admission. After looking at the mathematical precision that holds every atom and every galaxy together, it is hard not to feel that the cosmos is tailor-made. In science, this is sometimes called the Goldilocks universe. Not too dense, not too empty, not too hot, not too cold, but balanced just right for life to take hold. But this is where physics slows down and philosophy steps in, asking a question that splits some of the sharpest minds alive. Is the universe perfect because it was made for us, or does it only look perfect because we happen to be here to notice it? To grasp the dilemma, consider an idea known as the Anthropic principle. Picture a fish living in a puddle left behind after a summer shower. The fish looks around and thinks, "How astonishing. This hollow in the ground is shaped exactly for me. The depth is just right for my fins, and the water is the perfect temperature for my skin. Clearly, this puddle was made for me." From the outside, we can see the mistake. The puddle did not adapt to the fish adapted to the puddle's conditions. If the hollow had been different, that fish would never have existed, or it would have been something else entirely. That is the weak anthropic principle. Our existence acts like a selection filter. It is not that we were granted divine luck. It is that only in a universe with these particular laws could a creature arise that can ask why the laws are so precise. In countless other possible universes where gravity is slightly stronger, there is nobody alive to notice the difference. But there is a bolder, more unsettling version, the strong anthropic principle. It suggests the universe is not an accident, but has an inbuilt tendency that makes intelligent life emerge sooner or later. In this view, the cosmos is not a random puddle at all, but a system that somehow needs to be observed in order to be fully real. We become the means by which the universe looks back at itself. And yet, if we accept that such fine-tuning has purpose, we step onto ground that makes many scientists uneasy. If the constants of nature read like the parameters of a program, who wrote the code? Are we looking at the work of a cosmic architect, or is there a stranger technical explanation hiding behind our reality? What we call laws might be closer to settings than necessities, constraints chosen by a deeper framework we can barely imagine. So here is the final twist. What if this perfect universe is not a stage, but a simulation? A coherent run of rules playing out on a substrate beyond space and time? If so, the question shifts. Not only why the numbers are what they are, but what kind of reality produces numbers at all? And if observation is part of the mechanism, then our role is not accidental. We are the interface through which the cosmos becomes knowable to itself, a mirror that can wake up and ask what it is seeing and why today. When you stop and really look at the surgical precision of the numbers that hold our reality together, it becomes hard not to feel that we are living inside a system designed with intent. A modern video game offers a clean analogy. When a developer builds a virtual world, the first step is not painting landscapes. It is setting the environment variables, the hidden values that dictate how the world behaves. They decide how high a character can jump, how quickly objects fall, how much damage fire does, and how collisions resolve. Get one value slightly wrong, and the whole experience breaks. Set gravity too high, and the character cannot lift off the floor. Set it too low, and a single step sends them drifting upwards. The game becomes unplayable, not because the visuals are poor, but because the underlying parameters make coherent play impossible. The world collapses before the first player even enters. In our universe, the same logic seems to apply. Feynman's number, nuclear binding, and the early balance between expansion and gravity behave like configuration settings that make the match of life possible at all. What unsettles science is that, even with all our progress, no physical law forces these values to be exactly what they are. There is no obvious necessity for gravity to have the strength it has. The constants could have been different, yet the ones we measure happen to be the ones that allow the theatre of matter to work. That suspicion is what pushes some thinkers towards the simulation hypothesis. Under that view, the cosmos would not be solid matter emerging from nothing, but an extremely advanced software system running on a higher level substrate. The laws of physics would be closer to source code, and the constants of nature would be default settings entered before the start command was ever pressed. This also explains a familiar frustration. Physics can describe what happens once you insert the numbers, but it often cannot tell you why the numbers are those numbers. We measure them, we use them, and we build predictions around them. Yet the deeper why stays out of reach. If the constants are settings, that may be the point. You cannot derive a design choice from the behavior it produces. The cosmic programmer idea resolves fine-tuning immediately. The universe looks perfect because it was configured to be playable, but it also raises a sharper discomfort. Are we a conscious experiment running on an infinite processor? Or are we a side effect inside a program that does not even have us as its main objective? Many physicists resist this line of thought because it can feel like an easy exit that shuts down inquiry. If you can always say, a programmer chose it, you risk stopping the search for deeper explanations. So there is a third path. Our good fortune might not come from a perfect code written for us, but from a brutal cosmic filter, an enormous number of universes that failed, so that one could survive long enough for observers to appear. In that picture, reality is not tuned once by an architect. It is sampled again and again by chance. Most settings crash. Most worlds never produce long-lived stars, stable chemistry or minds. Only the rare survivors remain, and from the inside those survivors automatically look designed, because only a stable world can be noticed. So the mystery does not disappear, it shifts. If the universe is designed, we want to know by whom and why. If it is simulated, we want to know what substrate runs it. If it is one survivor among countless failures, we want to know what generated the space of possibilities in the first place. Either way, fine-tuning points to a strange conclusion. The deepest question may not be what the laws are, but why there are laws at all, and why they are the kind that let a mind wake up and notice them. If the idea of a simulation feels too artificial and the divine architect too mystical, science offers a third route, perhaps the most overwhelming of all, the multiverse. It says our universe may not be a one-off masterpiece or a solitary accident, but one page in an endless book of realities. In that picture, fine-tuning stops looking like a miracle and becomes a matter of statistics. It is not that the cosmos is perfect for us. It is that we can only appear in a cosmos that happens to work. The multiverse is not one single theory. It is a family of ideas meant to explain what our equations leave unexplained. Imagine a process that can generate universes in bulk, each born with its own set of physical laws, selected almost at random. It is a roll of the dice on a scale beyond intuition. In one universe, gravity is so strong that everything collapses almost instantly. In another, light never travels properly because the fine structure setting is wrong. If you could somehow survey that landscape, you would expect most universes to be sterile, failed attempts where the pieces never lock into place. By contrast, we are here simply because we drew the rare ticket that allows atoms to bind and stars to shine. That answer removes the weight of design, but it adds a different kind of loneliness. We would be the survivors of an immense cull, one success among a vast sea of universes that never made it past their opening moments. And the reason the universe looks made for life would be the same reason a winning lottery ticket looks meant to win once you are holding it. Still, not everyone is satisfied. Many cosmologists object that the multiverse feels wasteful. It seems extravagant to spend countless dead universes to get one living one. They also argue that it isn't science in the strict sense, because the other universes would be forever disconnected from us. If you cannot observe them, measure them, or test predictions against them, the idea risks drifting into the same limbo as religion or science fiction. At best, it becomes a framework. At worst, a story. Supporters reply that the multiverse is not pulled from thin air. Certain models of cosmic inflation naturally produce many bubble universes, each with its own local conditions. In quantum physics, many worlds' interpretations point to branching histories whenever outcomes diverge. None of this proves a multiverse, but it shows why the idea keeps returning. It tries to explain fine-tuning without invoking intention. It also offers a testable hope. Indirect signs in the background structure of our universe, subtle patterns that might betray collisions with other bubbles in the distant past. Even a negative result would teach which stories nature will not support. So the question still hangs in the void. Is the cosmos the whim of a god, the code of a simulation, or the outcome of an infinite lottery? Perhaps one of these options will eventually give us a final answer. Or perhaps the truth is stranger than any category we have. Either way, thinking it through reminds us of something basic. Our place in space is not a right, but a privilege held together by invisible mathematical threads. And in the end, the most astonishing fact is not that the universe seems perfect, but that, against all expectation, you are here to notice it. And that concludes our video. If you enjoyed the content as much as we did, don't forget to subscribe so you don't miss a single episode. Leave a comment below. We'd love to hear your feedback and suggestions for future videos. And don't forget to turn on notifications to stay up to date with all our updates. Thanks for being part of our community. See you in the next video.